Okay, so good afternoon, everyone. So today we move to a new topic, nonlinear equations. And nonlinear equations, we will study like some well-known method, how to solve it numerically, bisection method, fixed point iteration, Newton's method, secant method, and Newton methods for system of equations. So give equation like this. So suppose you have a function f and you want to find x, so that fx equals 0. Okay, and so you've seen this one from high school already, right? So you have linear equation, you have quadratic equation, and sometimes you can solve polynomial of degree 4, but it's not always simple. And for degree 3, there is a formula, but it's complicated. But in practice, f can be more complicated than a polynomial. Okay, and then sometimes you have more than one equations. Okay, and you have more than one variables. So in this case, then suppose f, capital F, is a function, of n variables, x1 up to xn, and then it has n values, and then you try to find a vector x in Rn, so that when you plug in f of x, and you got a 0 vectors. And again, this f most of the time could be a nonlinear function. So now let me introduce you like the very first nonlinear equation was proposed by Kepler long time ago, maybe 400 years ago. And he came up with this equation when he tried to observe the sky. Yeah, so he observed the sky, and so there is so if you study physics, and there's a Kepler law, right? So it's about the motion of the a body in space, and then he came up with this equation. So now, I'm not very good at physics, but essentially the equation is like this. You see, x minus a sine x equal b. So you see x here is the unknown, and sine x. So you see this is a nonlinear equation, and there's no formula for you to get out the solution easily. Okay. So the a and the b are the some some parameters that correspond to the orbit of the object in space. Okay. So anyone study physics here? Anyone? Have you seen this Kepler law? But anyway, you see, so it came up from astronomy, right? And this is a very simple one variable and one nonlinear equation. And so far, nobody can solve this by given an explicit formula. Okay. So then we have to solve it numerically. At least if you know how to solve it numerically, that is still good enough. And then system of equations. So here, you see, suppose you try to find x, y, and z, yeah, unknown. So that is satisfy 3 equations at the same time. So you see, this equation is a nonlinear, a system of nonlinear equations. Okay. And maybe something more familiar to you, because now everyone has an iPhone, right? So I think I cannot click the YouTube video now because I want to record the video and post it on YouTube. So I will put the link here, yeah. And then if you watch it, then it will explain to you how they solve the navigation equation in order to identify your position on Earth. So maybe let me draw pictures, yeah. So draw pictures, it's easy to explain. And you can watch the video later if you have time, yeah. So now, so maybe let me introduce the equation here, and then maybe let me draw pictures and So suppose you have your mobile phone here, yeah? So you stay here, somewhere on Earth. It's you, right? Or anyone, yeah, with a mobile phone. And now you want to find out your location, right? So how do you find out your location on your mobile phone? Well, you look at the Google Map, right? And actually what Google Map does is it will try to connect with 4 satellites in space. Okay, they call it GPS satellite. So GPS stands for global positional system, global positioning system. I think they have a constellation of over 70 satellites on around the orbits of the Earth, but your mobile phone needs to contact only 4 satellites. Okay. So then, you know, so now suppose your location is X, Y, and Z. Right, in space, yeah, your location can be denoted by X, Y, and Z. Then the first satellite will give their position. I mean, it is position in space, yeah. So X1, Y1, Z1, right? And then it can send you the time, you know, when it sends you a signals. So the like clock stamp, you know, the time stamp. So when you ask for signals from this satellite, it can send you a signal with a timestamp on it. You know, like suppose you ask the satellite right now, then it sends you the time is 1:07. Và xuyên đến nhiều Sydney time, but it could use you know, London time. And then you have to contact another satellite, and that gives you its position as well. So X2, Y2, Z2, and T2, right? Look it up. And then similarly, the third satellite send you X3, Y3, Z3, T3. Okay. And the fourth satellite gives you its positions. Okay. So now you have 4 pieces of signals, 4 signals from 4 satellites. And now you try to identify X, Y, and Z. Okay. So now, see, now when it sends you, when it sends you a signals, when the satellite sends you signals, then, you know, in your mobile phone, you have a clock, right? So you know that you have the time you receive the signal. So suppose TR is the time you receive the signal. So TR is the time you receive the signal. Okay. And then, you know, I mean, every device has some bias, some bias in the device. What is the bias? The bias is the difference between the clock in your device and the true clock. You know, maybe the true clock, the atomic clock say that now it's 0 second, but in your device, I mean 0 hours, 0 second. But in your device, let's say that 0 hours, 15 seconds, something like that. Okay, and this is unknown. This is unknown as well. Yeah. So you see, now you have 4 unknowns: X, Y, and Z, and B, right? You have 4 unknowns. And now how do we set up the equations? Well, so assume that, well, maybe not assume, but the fact is that the signals, okay, can travel as fast as the speed of light. Yeah. So then, so what is the distance from, say, the first satellite to you? The distance, say this one, yeah, this distance, yeah, D1, yeah. So you remember what is D1? So D1 is the distance between the first satellite to you, right? Yeah. Then it's just given by, you know, maybe you remember formula in your high school year, so you can take the difference between x, the difference between y square, and then the difference between z. Okay, and then you take the square root. Okay, so this is the distance between 2 points in space. Yeah, and then the distance here. Okay, so the distance equal the speed multiplied by the time it travel. Yeah. So the speed is the speed of light. Okay, the speed of light or the speed of electromagnetic signals. Yeah. So this one, speed of light or speed of signals. Yeah. And then remember you have the time. So what is the time? The time is the time you receive the signals. Yeah. Plus the bias. Bias is the difference between your clock and the true clock. Okay, because there should be, so in the signals they have a clock as well, and they have to compare their clock with the true clock somewhere, some atomic clock somewhere. Yeah, and then this one is just the difference. The time is like the difference, the time it travel, just the difference when you receive the time minus t1. T1 is when the satellite send you the signal, the timestamp. And you see now you have 4 equations. So you have D1, then D2, and up to D4, right? So D4 will be x minus x4 plus y minus y4 square plus z minus z4 square equals c dr plus b minus d4. So you have 4 unknowns. Yeah, you have you just similar. So you have 4 unknowns, right? And you have 4 equations. So that's why you need to connect to 4 satellites. And then it solves the equation for you very fast inside your mobile phone. Then it will map the coordinate to Google Map, and it pinpoint your location on the Google Map. Okay, so that is how Newton methods are used inside your mobile phone, and it did it very fast, so you don't know it. You don't know exactly, how fast it did the calculation. It did very fast within a fraction of a second. And you just see your location on Google Map, and that is the correct navigation satellite. Okay, so sorry, navigation equations. And see, so now we go back to the slide. Yeah. So the x, I, y, I, z, I, and t, I are Cartesian coordinates of each satellite, right? And t, I the time when the signals are sent, the timestamp. Yeah. And then the time received is the r, right? And the b is the clock bias, the clock delay between the receiver clock and the the true clock somewhere. Yeah. And then the message travel at the speed of light. So what is the speed of light? Very fast. Yeah, 300,000 kilometers per second. So then you have 4 equations. Well, this one I just squared, but before I wrote a square root, but now you can square it. Sorry. And this is the equation that determines the location. So now we go to the very simple method, how to solve a nonlinear equations. Okay, so it's a bisection method. So now bisection method look like this. So suppose I draw pictures, quick explain by pictures. Yeah. So now the bisection method work like this. So you suppose you have a function f, yeah, and a function f maybe look like this. Okay, so the 0 is right here. So so now, you know, maybe I start with the interval. So the interval is a, right? Maybe a0 b0. So a0 b0, right? So this is the first interval. Then I compute the midpoint. Compute the midpoint, yeah. So I compute this one is my x0. So x0 will be 1/2 of a0 plus b0. It's the midpoint, right? And then, you know, now you check. Okay, so first we have to make sure that fa0 and fba0 are opposite signs. So when you multiply it, then it should be a negative number, right? And then now you find the midpoint, right? So find the midpoint and you check again. So what is a0 and f of x0? So if a0 and f of x0 is opposite signs, then you choose this is your new interval. So this is your new interval. This one is a1 and this one is b1, right? And then you do it again. Now you compute x1. So you compute x1 is 1/2 of a1 plus b1, and so on. And you see, I mean, your interval just got zoom in the 0, right? So until you get to some tolerance, and then you stop, right? And that is a bisection method. And you see, bisection method is like every time you just cut the interval into half. Yeah. So now what is the assumption? What is the assumption that we have? Well, maybe we can talk about assumption after this slide. Yeah. So now if I write down as algorithm, then it looks like this. Okay, so you find the intervals a and bn. So that fan and fbn opposite signs. So you multiply, then it should be negative. Then you find the midpoint. And then if, you know, you find an midpoint xn has opposite sign, this one will be your new interval. Okay. So, you know, it could be the left intervals or it could be the right intervals. Xn, Bn, you know, have opposite signs. When you choose, this is your new intervals. And then if fxn equals 0, then stop. But, you know, more practically, you just said that fxn absolute value less than some epsilon. Okay, could be machine by epsilon, could be some tolerance you gave when you stop the algorithm. Okay. So now, you know, I mean, if you haven't found the 0, then you just go back to step 2. You find another subintervals and you do it again and again, right? Until you got the solution. So now, what assumption do we have to assume on the function f? You know, so or why does this method work? Why does bisection method work? So what assumption you have to put on the function f? Anyone? So this is the yes, continuous. It has to be continuous, yeah. Because if f is not continuous, if it's broken somewhere, then, you know, I mean, your subintervals might not contain the 0, right? One can go up to infinity, one can go down to minus infinity, right? And what if the function doesn't cross the x-axis? Well, that's the x cross the x-axis is this assumption. we have to start at something like IN and BN have opposite signs. So that means one is below and one is above the x-axis. Okay. So what theorem? What theorem that gives you that if one value above and one value above and one value below the x-axis, then f must have a zero in between. And what value, what function, I mean, sorry, what theorem is that? Yes, intermediate value theorem, yes. Okay, so the intermediate value theorem says that if the function is continuous over a and b, fa and fb opposite sides, then it has a zero in between. So you see, so this method works based on the intermediate value theorem, okay, and the assumption that f is continuous. And now what is the conversion rate? Well, so what is the conversion rate? So every time you reduce the interval by half, right? Yeah. So you start with a and bn, and every time you just half the size of the intervals. Okay. So the conversion rate will be about 2 to the minus n. Okay. So now this is the MATLAB script how to use bisection method. So you can see that you know, I mean, here I just take f to be the function x minus cosine x, the Kepler equations, yeah. And then, so because I don't know how many iterations, so I just use a while loop, okay. And it depends on how you want to set up the terminal condition. But in this case, I just set a flag, you know, a flag will be raised if I found the zero, right? So if absolute value of fxn less than epsilon, so epsilon here just machine by epsilon, then I raise the flag, okay? And if I raise the flag, then it will stop doing the iteration. And now, you know, if I and xn less than zero, then you choose b to be xn. And if xn and b opposite sides, then you choose a to be xn. So you see that even I have an and bn in the algorithm, yeah, but in the program I just reuse the variable a and b again and again. Okay, so I just have a, b, and xn. I just recompute it again and again. Okay, and you've seen this technique before, right? So, and you can run it. You can run it, and you can see that it gives you the zero of the function f. You know, after maybe say 10 iteration, you have to check it. And you see the conversion. You see, so the bn minus an. You know, every time you just half the interval, initial interval. So b1 minus a1 just 1/2 of b0 minus a0. So b2 minus a2 just 1/2 of a1 minus b1 minus a1. And so if you iterate it, then eventually bn minus an is just 1/2 to the n of the initial interval. Okay, so that is how you get the conversion of the method. So usually the conversion is slow. Okay. Okay, so now another method. So now suppose I want to solve this equation. X is e to the minus x. Okay. And now, you know, you can plot it. You can plot it. X is the line that go 45 degrees from the origin up, right? And e to the minus x is just going down like from 1 to 0, right? And then it will cut each other. And now suppose I start with initial guess like this. I start with x0 equals 0.5. Then I compute x1 by f of x0. Okay. And then x2 is just f of x1. And so on. x3 just f of x2. And you see that, you know, after about 16 times, then it starts staying at the same point. Okay, and we call it a fixed point. And maybe if you look at the pictures, so the line y equal x is the blue line, yeah? And the green curve is y to the minus x. And you start from 0.5, yeah? Then, you know, I mean, you compute e to the minus x1, right? Then you project through the y equal x, then you got x1 here. So the first dot is x0, and then the second dot is x1. And then you do it again, okay? So you compute the value e to the minus x1, and then you project down and you got x2, and so on. You see, so it's like a spiral, right? Like a spiral, and it will eventually, it will go to the intersection of the two curves, yeah? So you, well, I mean, you can use a for loop like this, because in this case, we don't specify the tolerance. So you can just, you know, do 15 iteration, yeah? And even in the program, I mean, in the algorithm, we write xn is f of xn minus 1, but you can reduce the variable. Okay, so I start with x equals 0.5, and then I compute f of x, and then I put it back to x again. I just do it again and again. And you know, if you run it, then after a few iterations, it will stop. It will fix at some point. Why you use a for loop? No, I mean, there's no reason here, because I in the algorithm, I don't say how do I stop the algorithm. Okay, I don't say how do I stop the algorithm. So then I can use a for loop or while loop. Is up to me, right? If I give a tolerance, yeah, then you need to use a while loop. But here, because we don't specify the tolerance, we just say that I want like 15 iteration, then I just use a for loop. Okay, so it's not a it's not something like, you know, we we just specify the number of iteration. Okay, so then, I mean, it's not very rigorous here, but I just want to show you how the algorithm works. Yeah. Okay, so now in general, we start with the initial guess x0, right? So first we have to have the function in the correct form. Yeah, you try to find the equation, sorry, you try to find the solution of x equals g of x. So remember, initially we have f of x equals 0, but now first you have to notice that this one is x equals g of x. Okay, and you want to find, you know, x star. Let's solve this equation. So x star equals g of x star. So you choose the first guess x0, and then xn plus 1 just equal g of xn. Yeah, and then, you know, up to some point, if you see that x star equal gx star, then you got it a fixed point. Okay, because now, you know, you cannot do anything, right? Just you put gx star, just stay there. So now, how do you know whether this method converges or not? So now, suppose I try to solve x equal e to the x by fixed point iteration. So what happened? Do I have a conversion or not? So you can play around with this to see whether you have a conversion or not. So if I have x equal e to the x, no conversion. So what does it do? You can try to put in MATLAB or calculator. Or... So what does it do? I mean, if you have x to the e to the x, have you tried? Just get bigger, right? So you can try to write out a simple Maybe let me try to write down a simple MATLAB script. So now now let me share my MATLAB script. Okay, so this one I just have I just have x is 0.5, right? And x equal e to the x, and I let it run. And you see, I mean, after like 5 iteration, it just blows up to infinity. Yeah. Just get bigger and bigger, and after 4 iteration, just blows up to infinity. I mean, if I put minus x here, then everything is okay. It just stay at a fixed point. Yeah. So 0.5671. So you can see that, I mean, not every function gx give you a conversion. Yeah. So you can play around with a few more examples and you can see that. And now, how do we know? How do we know that give you a function g of x? How do you know that the fixed point iteration will converge or not? So now let me introduce some theory. So suppose now I define the errors. Okay, so I'll define the errors to be the difference between the approximation xn and the solution x star. Okay, then what is my en plus 1? So en plus 1 is just xn plus 1 minus x star, right? But by the fixed point iteration method, xn plus 1 is nothing but g of xn. Yeah, that's how you define it. And x star, remember x star is a solution of the fixed point iteration. So x star equal g of x star. Yeah. And now, so xn, okay, xn. So when you write, you move x star to the left, then you got xn, it's just en plus x star, right? So I write xn, it's just en plus x star. And then minus x star. So now what is the next step? So what I'm trying to do is I try to relate en plus 1 with en. Okay. And so the first step is I just use the definition of the iteration and the fixed point definition. And then I get something like this. And now I want to relate this with en. So then what should I do? Anyone? Any theorem that come up to your mind that somehow, relate this one to en? Any theorem, any calculus theorem? So what is the, suppose you have a GA minus GB, right? And you want to somehow express it in terms of A minus B. Then what theorem that give you that? Mean value theorem. Yes, very good. So the mean value theorem can show you that, you know, this expression is just equal G prime, you know, at some point time En, all right? Yeah. Or, you know, I mean, another way is you use that as function. So it's the same, you know, the same as at the mean value theorem. So the mean value theorem or the Taylor expansion, you know, can somehow relate this one to En. So if I use Taylor expansion, then I I just, you know, like rewrite G x star plus En by, you know, Gx star plus G prime x star En plus higher order terms. And, you know, I mean, if I plug it in here, then the Gx star got cancelled, right? The Gx star got cancelled. Yeah. And then I got En plus 1 equal this expression. And you see, I mean, you can use mean value theorem directly, and then you don't have to worry about this extra term. But here, then you have G prime at some point xi between x star and x star plus En, right? So you get the idea, right? So then if I ignore the higher order terms, then En plus 1 roughly equal G prime x star En. Okay. So again, if you use mean value theorem, then you arrive at the same thing. You know, En plus 1 approximately equal G prime x star En. Okay, so this one just mean approximately. Okay, we ignore some smaller errors. Yeah. And now what what condition you should have on G prime x star so that the method converges? So what condition should I put on G prime? Okay, so maybe I should give some example. It's easier to give example rather than look at the formula. So now suppose I write some example, right? So now suppose I have, so remember, so suppose this one is my x star, right? Yeah. And this is my x1. And this is my x2 and so on. Yeah. And now what is the error? So the errors, so the E1, okay, equal x1 minus x star. Okay. And the E2 is x2 minus x star, right? And now you want roughly, you got E2 is roughly about G prime x star of E1. Yeah. Somebody say G prime less than 1. Yeah, it's correct. Yeah. So what you want is you want G prime less than 1. Then E2 will less than E1, right? So get closer to, so you want Xn get closer and closer to X star, right? So it means that every time you want the errors get smaller and smaller. And if the errors get smaller and smaller, it means that, you know, E2 has to multiply with something less than 1 of E1 to get it smaller and smaller, right? So then what you want is G prime of X star in absolute value has to be less than 1. Okay, so then the method converges. Otherwise, it just gets bigger and bigger. And I mean, if it gets bigger and bigger, then it goes further and further away from X star. Yeah. So you start at X1 here, and x2 just go further away, and x3 go further away, then it diverges. So that's exactly what is going on. So now you expect convergence if the absolute value of G prime less than 1. And you see that if G equal e to the x, right? Then x star is, say, you know, in the previous problem, you have well, e to the x and x, it doesn't cut each other. So, but you see, like e to the minus x, yeah. And if you put in e to the minus 0.5, then absolute value will be less than 1. So the first example converges. Okay. So in practice, unless G prime is very small, then the conversion is very slow for this method. So we should apply other methods. Okay. And so now we consider equation. So suppose you got x equal 1 over cosine, hyperbolic cosine of x. Okay, so exact solution is this x star, and then we got g of x is 1 over hyperbolic cosine of x, and g prime, you plug it in, then g prime, you see, you plug it in x star, then absolute value will be less than 1. Then I mean, you plug it in and you can see that it converges, so the errors get smaller and smaller. The errors get smaller and smaller, and xn, it gets closer and closer to the solution, right? So the exact solution is 0.765 something. And now after 7 iteration, it's 0.0764 something already. So for example, 4, it was in the starting point. A very good question. So, well, so if you try another starting point, well, we can play around with that. So if you start with a different, so it doesn't matter what initial point you use. It's correct because I mean, if you plug it in here, yeah, g of x here, the e to the x, right? So e to the x, you see that if x bigger than 1, no, actually e to the any power is always bigger than 1, yeah, because e to the 0 is 1 already, so e to the any tiny number is still bigger than 1, yeah. So then it doesn't matter what x0 you put in, yes, you still diverge, yeah. That is a very good observation, yeah. But how about the previous one? Suppose I put in this one. Okay, what happened if I put in not 0.5? Yeah. Then now you will see that it will converge, but the number of iteration might be different. Okay, so we can try it. I mean, if you want, we can plug it in MATLAB and see right away. Yeah. So suppose I plug in MATLAB. So suppose I started at 0.5, right? Then I got 0.56 after 14 iteration. Now what happened if I put in like 1.5 and I run it? So see, if I start at 1.5, then it still go to 0.56 something, right? So you see, it doesn't depend on the iterate. I mean, sorry, it doesn't depend a lot on the initial guess. Yeah. Maybe it take a few more iteration to get to the fixed point. But the iteration, I mean, just move it to the correct answer. Okay. Yeah. So does it make sense? So now we go back to the slide. Yeah. So you see that what we want is just G prime at a fixed point less than 1. Then you can have a conversion of the method. Okay, so now we move to another method, Newton method. So the previous method, okay, are slow in the sense that it took many iterations to converge to the correct solution. And so now Newton method is a method, one of the fast methods to come up with the equation. And we will see why it's a fast method, okay? But now before doing a Newton method, so let me do a small squeeze, yeah? So because it will help you to understand the Newton method easily. So now if you go to Moodle and so before we go to Newton method, yeah, we go to Moodle, okay? And then if you click on this interactive, so there's a Newton method here, okay? Click on it, and now there's a simple question. So suppose you draw a curve x squared minus 2. Then you draw a tangent line at x equal to the curve. And now find out where does the tangent line cut the x-axis. So there's a few choices here. So can you draw the curve, or you do some calculation and see like what value can you get? Okay. So I can show you the results and see how people come up with the solution. And we can go back to Newton method later. So far, no responses. So you get to the, I'll let you have a few more minutes. So this one is the responses. So we don't have responses. And okay, so one response is. So this is the question. You draw the curve x squared minus 2. You draw a tangent line at x equal 2. And then try to find out where does the tangent line cut the x-axis. We have two responses, 1.5. Okay, so how do you get 1.5? So 3 people said that 1.5. Okay, so let me do a drawing and check whether it's correct. Yeah. So you have well, maybe we can check it later, but essentially, you do the calculation and see whether it's 1.5 or not. Okay, so but we can check this later. So now go back to the slide. Yeah. So now, or maybe we can check it now. Yeah. So now suppose you draw a curve, right? The curve is x squared minus 2. So then you have so if x equals 0, then y equals minus 2. Yeah. And if x equals 1, then you have 2 here. So if x equals x equal 1, then you have minus 1, right? And if x equal 2, then you have 2, right? So something like this. So the curve looks like this. So parabola, right? So this is 1 and this is 2. Okay, so this is 2. And now what is the slope of the curve? The slope of the curve is f prime at 2, right? And f prime at 2 is just x square. I mean, x square prime is just 2x, and 2x at 2, which is equal 4, right? So the slope is 4. So we know the slope is 4. And we know that, so the function will go through 2 and 4, right? So because if you put in, well, actually it's not 2 and 4, 2 and 2, right? So because f of 2 is just 2 square minus 2, so just 2, right? So now the function is y equal 4x plus b. And if you plug in x equal 2, then y equal 2, yeah? So then b has to be equal for, no, sorry, 2 minus 8, yeah? Equal minus 6, okay? So the line is y equal 4x minus 6. And now you set it equal 0. So you set it equal 0, then you find the intersection here. Then x is just equal 6 over 4, or it's just 3 over 2, which is 1.5. Okay, so you got the correct answer is 1.5. And so now essentially that is Newton method. So if now I go back to the slide, you will see that is essentially that is the Newton method. So now we try to solve this f of x equals 0, right? And then, you know, I mean, use Taylor expansion, you expand. So this is another view to look at the Newton method. If you look at the Taylor expansion of the function f around the point xn, okay, then ignore the higher order terms, okay, ignore the higher order terms, then you just have f of xn plus f prime xn x minus xn equals 0, yeah? So assume that f of x equals 0, right? So assume that f of x equals 0, and then you have you have 0 here, yeah? And then you see when you solve this, okay, then you can label this is the next iteration xn plus 1. Okay, so you rearrange this. If you move this one to the left, then you got minus fn, and then you divide it by f prime xn, and then you plus xn, then you solve this, yeah? So xn plus 1 equal xn minus f over f prime. It's just the consequence of rearranging this equation. And then this is exactly the pictures, okay? So you start at the point xn and you make a tangent line. You write a tangent line, and then you let the tangent line going down to the x-axis, and we've got at xn plus 1. Okay, so that is the Newton method. So maybe we take a break for 5 minutes, and then I will go back to this. Okay, so I will pause the recording. So that is essentially the Newton method, and we will talk a bit more about this after the break, 5 minutes break. Okay, so we start again with the Newton method. So now if you, so let me draw pictures, yeah. So now suppose you have a curve like this, okay? Then suppose to cut at some point here, yeah. Cut the x-axis, and now you start at xn. Okay. So now this is the equation of we try to find out the equation of the tangent line. Okay, that so maybe this is a function f, yeah. So the equation of the tangent line, okay, that go through the xn and f of xn. So this point is f of xn. Okay, so equation of the tangent line will be equation of the tangent line at xn will be y minus f of xn equal f prime xn x minus xn, right? Because I mean, if you put x equal xn, then you got y equal fn, yeah. And the slope of the tangent line just equal f prime at xn. Okay, so this is your equation. F xn, f prime xn, x minus xn. And then you want to find the intersection between the tangent line and the x-axis. You just set y equals 0. Okay, you set y equals 0. Then x equal xn plus 1. Okay, so then you got fxn plus f prime xn plus 1 minus xn. So therefore this point is xn plus 1. Okay, and you rearrange it, then this one is just xn plus 1 equal I mean, you rearrange it, right? So this one is xn plus 1 minus xn equal minus fxn divided by f prime xn, right? And then xn plus 1 equal xn minus f of xn divided by f prime xn. Yeah. And this is a formula for Newton method. And so it's easier to remember the pictures rather than the Taylor expansion. Okay. So because the pictures, you know, like show you how to find out the formula, because you don't want to remember the formula, right? You want to remember the process, how to derive the formula, and you can reconstruct it easily. Okay, so this is xn plus 1 equal xn minus f xn over f prime. And suppose I implement this method. Okay, so we return to the equation x is 1 minus hyperbolic cosine x. Then the solution, you know, I mean, this equation is the form x equal g of x, but Newton method asks you to write down in the form f of x equals 0, right? So you have to rearrange it. So you cross multiply, then f is just equal x hyperbolic cosine minus 1. Okay, so then you implement the Newton method. So then you see that after only a few iterations, after 6 iterations, you know, it go down to the very close to machine errors. Yeah. So 6 iterations, it go down to machine errors. So before, for the fixed point iteration, if you go back to the fixed point iteration, the same the same equation, right? After 7 iteration, you know, it's still like 10 to the minus 4, right? So you see, so Newton method is faster than fixed point iteration. Yeah. And now you can implement the Newton method by MATLAB like this. So you define the function f, okay, like anonymous function x hyperbolic cosine x minus 1, and then you define the derivative as anonymous function as well. So this one you do it by hand, you know, apply the product rules. So product rules, then the derivative of x is 1, so you got hyperbolic cosine here. Then the derivative of cosine is just hyperbolic sine. So this gives you the second term, and you. So this is the formula for Newton method, right? So remember, we reuse the variable x. So xn plus 1 or xn, you know, you just put it back into x, and you got this formula. X equal x minus f of x over df of x. Okay, so now fixed point iteration and Newton method, they are related, because if you look at the formula, okay, so this is like xn plus 1 equal g of xn. Yeah. So then this is exactly here. So if you put g of x equal x minus f over f prime of x, then it's just a fixed point iteration. And then now the problem is when you take g prime, okay, when you take g prime, so you apply the quotient rules, then you got this f double prime over f prime square, okay. Then if f prime is non-zero, yeah, if f prime non-zero, then f of x is equal to 0, because you assume that x is a 0 of the function f, right? So then g prime at x star is always equal to 0. So it means that the ratio en plus 1 over en, you know, always less than 1. So it's always convergent. Okay, it doesn't matter what the function f is, right? So that is the implication here. So now the problem with Newton method is it's very sensitive to the initial guess. Okay, because now if you look at the pictures, go back to the pictures, you can see that if I start x0 here, right, then when I draw the tangent line, then it will cut all x. Okay, but what happens if I start at some other point? What happens if I start at, say, here, right? Then, or even here, the tangent line, if it parallel, you know, suppose this function going down to like x squared, right? And, you know, somehow I just, tangent line is parallel to all x, then I have no convergence. So that's why Newton method is very sensitive to the initial guess. Okay. So now what I want to show you that the Newton method converges faster than the fixed point iteration. So remember, before, for fixed point iteration, we showed that en plus 1 is a constant time en. Okay. But Newton method, we can show that en plus 1 over en square, okay, go to some constant. And now I can show you what faster. Maybe we do some example. So So before we prove the theory, yeah. So let's do some simple numerical example. So suppose I have a table like this, yeah. So maybe en plus 1 equal say 0.5 en, yeah. Okay, so this is fixed point iteration. And now suppose you start with E0 equal, so remember en is just the difference between x star minus xn, okay? So this is exact solution and this one approximate solution. So what you want is you want en go to 0, right? Then you have a conversion. So now suppose I start with E1, so E0 equal 1, okay? Then E1 will equal 0.5, right? And E2 will be 0.5 times E1, which is 0.25, okay? And then E3 is 0.5 of E2, which is 0.125, and so on, right? You see that every time the errors just get half, yeah? And now for Newton method, so now suppose Newton method, I got En plus 1 equals 0.5 En square, okay? So notice the square here. So this is a Newton. So I got E0 equal 1 as well, right? Then E1 equals 0.5 times E0, so it's still 0.5. But then E2 is 0.5 multiplied with E1 square, right? Which is 0.5 times 0.25. So this one is 0.125 already. So you see E2 is already 0.125. And you can see that, you know, the further you get, you know, because the square here, so it go down much faster. Okay. So that is the effect of the square here. So that's why the Newton method is faster, going down faster to 0. I mean, the error is going down faster to 0 and the fixed point iteration. So now we have to prove why is the case. So now we use you know, Taylor polynomial expansion again. So now why do I get this? So now what is the Taylor formula? So anyone remember what is the Taylor formula? Anyone remember what is the Taylor formula? So why do I get this one? So anyone remember the Taylor formula, Taylor expansion formula? Yes. Okay. So now I want to show you that the Taylor formula can be used to derive this one. So let me go back to the piece of paper. Yeah. So so now, so like you said, right? So now suppose I have a Taylor formula is just the sum of f of x0 plus f prime x0 over 1 x minus x0 plus f double prime x0 over 2 x minus x0 square plus so on, right? So you got f to the n over x0 over n factorial x minus x0 to the n. Okay. But no, actually this one is f of x around x0. Okay. But now I want to choose x to be x star. Okay. So what is the consequence? The consequence is f of x star equals 0. Okay, because x star, remember, is a solution of the of the function f. Okay, so I choose x to be x star. Then instead of x0, okay, I let it to be xn. So remember, xn is my nth iteration of the Newton method. Yeah. Then what I have is I have f of x0. Okay, what is happen to be equal 0, and then this one equal f of xn. Yeah, and this one will be f prime of xn, and this one xn minus x0. Okay, well, actually x0 equal xn, so actually this one is xn and x to be x star. Sorry. Okay, and then plus f double prime of xn over 2 x star minus xn squared, and so on. Okay, plus f triple prime xn over 3 factorial x star minus xn cubed, and so on, right? But remember how we define the en. So if you remember before, we define en to be xn minus x star. So you define en in the theorem, we define en to be xn minus x star, right? So then this one will be minus en. This one will be minus en. Okay, and this one will be plus en because, sorry, plus en square, because you got a square here. And this one will be minus en cubed, and so on. So you get the formula, right? Yeah. So that is how I get the formula in the slide. So now if I go back, so here, so remember we define errors en to be xn minus x star, and x star is the solution of f of x equals 0. So you use the expansion around xn, okay, and you plug in x equal x star, what is f of x star equals 0, then you get this equation. And now remember the remainder, the higher order terms, I just use a big O notation. So the big O notation here is just umbrella. Let's say that all the remainder terms can be bounded by en cubed in absolute value multiplied by a constant. And for now, I just ignore it. Okay. Yeah. So far so good, right? So this one is, remember, this is a minus en. Okay, and this one is a plus en square because the minus got square. And then now you just take the formula xn plus 1 equal xn minus f xn over f prime xn. Then you take, xn, en plus 1 is just xn plus 1 minus x star, and en is xn minus x star. So then you got this equation. Okay. Yeah. And so now the next step is you just cross multiply. So en multiplied by fn. Okay. So you cross multiply here, f prime xn here minus fxn. And then now you look at this equation, f prime en minus fxn, and you compare with this one. Okay. And then you see that, you know, this one, when you move the highlighted terms into the left, and you got exactly these two terms. Okay. And that's exactly what I put in here. Okay. So now what is the next step? So next step, I just divided the left and the right by en square. Right? So now if I divided the left and the right by en square, yeah, then divided en square, then you see this en square got cancelled. And this en cubed divided by en square just give me en. Okay. And now if xn go to x star, then en go to ens go to what? So if xn go to x star, then ens go to what value? 0. Yes. Remember, errors, it's just the difference between xn and x star. And xn goes to x star, and n's go to infinity. Okay, so xn go to x star. And so that is the theorem. So the theorem can be proved in one page. Yeah. So that is what I proved. I just proved that en plus 1 over en square go to, you know, 1/2 f double prime over f prime, the point x star. Okay, because here xn go to x star. And you see that the errors of the Newton method, you know, is of order 2, right? Because that's square here. So now if I look at this function, f is e to the x plus logarithm x, then if I apply the Newton method, I can compute en plus 1 over en square. And you see that, you know, I mean the ratio en plus 1 over en square, you know, it very stable at -1 point something here. Yeah. But now what happened at the very last step? What happened? Suddenly just become very big. So why is that? Why in the very last step suddenly it become like 1,000,000 or something? So the first few steps, everything is okay. Newton method is faster than the bisection method. Yes. Remember bisection method, the conversion is 1 over 2 to the n. Right? So the error just give half every time. You know, so you got 1 and then 0 0.5, 0 0.25, 0 0.125, so on. But now back to this table. So what happened at the end? You know, we see that en plus 1 over en square, it's very stable after a few iterations, but suddenly it just goes up. So does it mean that the theorem is wrong, or so what is going on here? It is because the denominator is very small. You are close, but smaller than what? Was small, but you know, we consider, remember, en is small as well. We consider the ratio. So smaller than numerator. Yeah, but we consider the ratio. So now maybe pay attention to the last value. So what's so special about the last value? What's so special about the last value? Yes, smaller than epsilon, right? So you see now the round off errors can interfere with the theory of the Newton method. You know, whenever you have something less than epsilon, you know, you can have some round off errors, and then your theory is no longer applicable, right? We saw it before. So whenever something less than epsilon, you have to be cautious. Yeah. So the theory is still correct up to a certain point, right? 10 to the minus 3, 10 to the minus 6, 10 to the minus 12. But when it hit the epsilon, then be careful, okay? Okay, so now usually, you know, like Newton method converges whenever the initial guess is very close to the exact solution. But if you choose the initial guess not very well, then the method can diverge. So that's the drawback of the Newton method. Yeah. So many applications, you know, you try to solve f of x equals 0, then you want that, you know, the method is always converge. You don't want to diverge algorithm. And then sometimes, you know, I mean, especially in engineering application, you don't have the derivative. You have the values of the function f only, you know, and Newton method require derivative. Yeah. So some function, suppose we know the function already in the formula, we can find the derivative. But if the function comes from another program, you know, especially in engineering, you know, it's come from another software, then how can you find the derivative? Okay. So then people come up with another method try to avoid the derivative, which is the secant method. So the secant method, okay, you replace the derivative by this divided difference coefficient. And so remember the divided difference coefficient between the 2 points. Yeah, it's just the slope of the line that go through that 2 points. Yeah, so the slope is either different in x, sorry, different in y over different in x. Yeah, and then you replace the formula by xn plus 1 equal xn minus f over the divided difference. So now if xn is very close to xn minus 1, then the divided difference, right? The slope of the secant line is very close to the slope of the tangent line, f prime xn. So the secant method can be thought of an approximate Newton method. And you know, the secant method, it's just because it's just a slope of the secant line that go through the 2 points, xn minus 1, fx minus 1, and xn fxn. Okay, so the secant method doesn't require the value of f prime, but the conversion is a little bit slower than Newton method. It's still faster than fixed point iteration, still faster than bisection, but somehow a little bit slower than Newton method. So there's a trade-off. And for example, suppose we consider this equation again. So f is e to the x plus logarithm x. Okay. So if you apply secant method, you can see that you got up to 8 iteration before the error is smaller than epsilon. You know, before you have only 6 iteration or 7 iteration for the errors to be less than epsilon. But here, you know, it takes 1 or 2 more iteration. Okay. Okay, so now this is the proof. So how do we prove that the secant method converges? Okay, so this is the one slide how to prove it, and maybe it's better to do it step by step. Yeah, so now first we define the errors is en equal xn minus x star like before, right? But now we don't have en plus 1 over en squared anymore, but we have en plus 1 over en times en minus 1. Okay, and it still go to some number, some fixed number, f double prime over 2f prime. And we do it step by step. Okay, so the errors en plus 1 is, by definition, is xn plus 1 minus x star, right? And you replace xn plus 1 by the definition, right? So this one is the definition xn plus 1 minus x star. And now, so the xn here, okay, and the x star here, you combine it. So you got xn minus x star, you combine to a single term. Okay. And for this term, yeah, f of xn over the divided difference, I just minus f of x star. Okay. So why I'm doing this? Well, first, I know that f of x star equals 0, so I minus a 0, so it's still the same, right? But why I'm doing this? Well, because I want to use, you know, I mean the property, some property of the divided difference. So now I just make this one the same. Yeah, I just make xn minus x star stay the same. Okay. But for the second term, I just multiply and divide it by xn minus x star. Okay, multiply and divide by xn minus x star. So now I have xn minus x star is the common term. So xn minus x star is the common term, right? So I can take it to be common term right here. Then inside, I just have 1 minus, well, 1 come from here, 1 come from this one. Yeah, 1, yeah. And minus, okay, what left over from here? So what left over from here? I just, now if you look at this term over this, it will be just a divided difference over xn and x star. Okay, so this is a divided difference of xn and x star. Yeah, so this two term. Yeah, and then the denominator is still the same. So still f of xn minus 1 xn. Yeah, and then what is this one? So this one is nothing but en, right? En is xn minus x star, right? And now for the thing inside here, yeah, I just first I just cross multiply. Yeah, I cross multiply. So you have f of xn minus 1 xn minus fx star xn. After I cross multiply, I divide it and multiply by this term xn minus 1 minus x star. Okay. So then what do I have here? So this one is just en minus 1. Okay, just en minus 1. And then this one now is a divided difference over 3 points. Okay, so you see that this one is a divided difference over 3 points. Xn minus 1, xn and x star. Yeah, if you remember the divided difference. So this one gives you this term. Okay. And so now I have the en and en minus 1 on the right. And I can divide it. I divide it downstairs here. Then what I'm left over is just this divided difference over 3 points over divided difference over 2 points. Okay. And now my claim is when n go to infinity. Okay, my claim is when n go to infinity. then this divided difference over 3 terms just go into 1/2 f double prime of x star. And this divided difference over 2 terms just go to f prime of x star. So why is that? So why is that? Okay, so maybe we have to get our piece of paper. But you see the manipulation above is clear, right? You just look at step by step, yeah? Now I want to explain the very last step. How do we get this one? So now if you follow on the step, okay, then eventually you have to come down to this. So f divided difference of xn minus 1 over xn, yeah, is what? It's just f of xn minus 1 minus f of xn over xn minus 1 minus xn, right? And by the mean value theorem, so this one is just equal f of some xi, right? Xi is between xn minus 1 and xn. Yeah. So this one just mean value theorem, mean value theorem. And now what happens when n go to infinity? So when n go to infinity, then xn minus 1 go to x star, right? And xn go to x star. Okay. Then what happened to psi? Psi is squeezed between xn minus 1 and xn. So what happened to psi? Pynchon theorem, yes, the Pynchon theorem. Pynchon theorem, you know, so psi has to go to x star as well. There's a limit here that just go to the center. So this is a Pynchon theorem, yes. And you see, so therefore you have f of xn minus 1 xn, the divided difference just go to f prime of x star when n go to infinity. Okay. And then the next one is, how about the divided difference over 3 terms? So okay. So you see, remember there is a theorem. There's a theorem. Let's say that this one equal f double prime of xi over 2 factorial x minus xn minus 1. No, we just have this one. For xi is between xn minus 1 and xn. So what theorem is this? So what theorem that gives me the divided difference over 3 points? Just f double prime of xi over 2 factorials. So now if you go back to the previous lectures, yeah. So there's a mean value theorem for divided difference. Okay, so mean value theorem for divided difference. Okay, so this one, check check the slide of the previous lectures in the interpolation. Okay, just the very last theorem. Yeah. So so the theorem right before the errors of the interpolation. That's the mean value theorem for the value difference. Okay. And then, you know, now when you take n go to infinity and you apply Pynchon theorem again, okay, then this one will go to f double prime of x star divided by 2. Okay, and n go to infinity. Okay, so that is how I got the claim at the end. So that is how I got the claim at the end. Okay, so then you just got the limit. It's just 1/2 of f double prime over 2f prime. Yeah. So now we in MATLAB there is a function f0. So f0 it will use a combination of bisection and secant method and inverse quadratic interpolation. So inverse quadratic interpolation, we will talk about it in the tutorial. Okay. And then, you know, if you try to use f0 to solve the function f of x equals 0, then first you just define f as an anonymous function like this. Okay, for example, f is just e to the x plus logarithm x. So this is a natural log. Okay, then you give some initial guess. So you give the function f, then it gives you the 0. The 0 is around the initial, starting from initial guess. Okay, or you can give a interval. You can give intervals a and b, so that it try to find out the 0 inside that interval. So suppose I give like 0.1 and 1, and say from -1 to 1, sorry, -1, and this one 2 point something. Then you give f0 and give the initial interval, and it found the 0 for you. Okay. So how do we choose the method? So now we choose the method if we know the curve. How does it look like? Okay, and then if we see that the function changes sign at a 0, then maybe, you know, you use bisection method first. You find the region, right, that has a 0, and then, you know, you can use fixed point iteration, but only when g prime is a very small value. Otherwise, you know, it might be very slow. And then once you have a region that you have a 0, then you can use Newton method to find a very accurate solution. And if you don't have derivative, you can use secant method. Okay. So Newton methods requires 1 initial guess, but secant method you need 2 initial guess. Okay, so remember you have to give like x0 and x1, and then it will start doing from x2. Okay, and the secant method is preferred if evaluation of the derivative is difficult. Then you choose Newton method. Yeah. So then, how do you stop the method? Okay, so you can choose a tolerance. You can choose a tolerance tau, and then you can choose either, you know, a successive between 2 approximation. The distance between 2 successive approximation is less than tau, right? So remember, in this case, you don't know the exact solution, right? So you just look for the successive approximation, and if it gets smaller and smaller after every iteration, if it less smaller, then you cannot improve it anymore, right? So then you can stop after that. Or you see, if you know that the function f, and you can evaluate the function f, and if less than some tolerance tau, could be epsilon, okay, or multiple of epsilon, then you can stop. Or you can choose the relative errors instead of the absolute errors between the two successive iteration. And then you can give the maximum number of iteration as well. You don't want it to do the iteration forever. Okay, say maybe you do like 100 iteration and you stop. Okay, so now we talk a little bit about the order convergence. So now the order convergence, yeah, is the largest number new. Okay, well, new could be integers, but it could be non-integers. But as long as you have the limit of the quotient in absolute value, en plus 1 over en to the new, and if it equal beta, okay, then we say that the order convergence of the method is new. So then what is the order convergence of the fixed point iteration? So what is the order convergence of the fixed point iteration? Anyone? So if I use the fixed point iteration, so remember, that's okay, because we just discussed it like last hour. But remember, in the fixed point iteration, you just have en plus 1 equal g prime x star e to the n. Yeah. Then what is the order of convergence? Well, we can go back. Yeah. So we can go back. So the fixed point iteration, you just have en. Sorry, we just have en plus 1 equal g prime en. Yeah. In other words, you have en plus 1 over en equal g prime xn. Yeah. So then what is the order? What is the order convergence of the fixed point iteration? So you see, you compare, this is the equation, right? En plus 1 equal g prime xn en, yeah? And then you compare, yeah, 1, right? So you compare with this definition. Definition is just say that you take you just take yeah, you just take en plus 1 over en, right, power 1, right, equal g prime. So then you know that the fixed point iteration, the order just 1, right? So how about Newton method? So what is the order of Newton method, order of convergence? So what is the order of conversion of Newton method? 2, right? Just remember Newton method. Remember the theorem. The theorem just show you that. The theorem just show you that En plus 1 over En square. See, remember there's a square here. Yeah. The power here is the order of conversion. Yeah. And this one just order 2, right? So, so then how about the secant method? So how about secant method? So now the secant method is a bit tricky, but just make a guess. So what is the order of conversion of secant method? So here, see, the problem is for the secant method, you don't have a clear cut En plus 1 over En to some power, right? But you have something like this, En plus 1 over En, yeah? But you can make a guess, yeah? You can make a guess. Suppose, you guess that the order of conversion of secant method is a number, then what is the range of that number? Yeah, between 1 and 2, right? Because it's going to be slower than Newton method, so it's less than 2, but it will be faster than fixed point iteration, right? Because you have an extra term here, n minus 1, so it will be between 1 and 2. Okay, so it's a very good guess, yeah. And that is exactly what it is, yeah. So if you have nu equal 1, okay, then we say that the method has a linear or first order conversion. Okay, so just a terminology. And remember the constant here, okay, has to be less than 1. Otherwise, you don't have a, decrease of the errors, yeah. And if beta is close to 1, yeah, then the conversion is very slow, because every time you just make the errors get smaller, but very tiny bit. Okay, so like if the constant is 0.9, then you got 0.9, then 0.9 to the power 0.9 is very slow. And the fixed point iteration, so like we discussed, it has a linear order conversion. Order conversion is 1. Okay. And then the Newton method. Okay. So maybe we say that if nu is bigger than 1, and then there's the terminology said that is super linear conversion order, just bigger than linear. And nu equal 2, then it has a quadratic conversion order. And Newton method has a quadratic conversion order. Okay, if f prime, so remember this condition is important. If f prime is non-zero, okay, f prime of the solution is non-zero, then the Newton method has a quadratic conversion order. Because in the tutorial problem, you will see that there is a question when f prime of the solution equals 0, then the Newton method doesn't have the quadratic conversion order. So this assumption is very important, okay? And then for the secant method, we don't know, yeah? But people have proved that the order of conversion will be of order nu equal 1 plus square root 5 over 2. So do you recognize this number? Anyone? Golden ratio, yes, it's a good golden ratio, yes. See, the secant method is conversion is it's a golden ratio, so very strange. So maybe I think we should stop here, right? Because next time we are going to talk about Newton method for a system of nonlinear equations. But I think it's a good time to stop. It's a good place to stop here. So any question? Maybe let me stop the recording and So whether you want to ask anything.